Hello and welcome to this video about vector space proofs. In this video we'll be proving a theorem about the basis of a vector space in 5 parts. These proofs are starting to get very wordy and dependent on past proofs and non-intuitive, but I hope that this video can in some way help you to better understand this proof and put proofs like this together by yourself in future. We'll declare the set of vectors B to be a basis of the vector space V, and B has n vectors. In part A, we'll prove that any set of vectors that is a subset of V and that has more than n vectors is linearly dependent, which I'll write as LD. This means that one of the vectors can be written as a sum of the other vectors in this set. Then in part B, we'll expand this to say that any set with more vectors than any spanning set will be linearly dependent. This may be obvious, but if you want another theorem to use this, it would be better to prove it now, because this would avoid confusion in the proof. Then we'll prove this, which uses part B. Then we'll prove this statement, which says that there's a limit to the amount of vectors in a certain set. Then finally we'll prove this, which is what we're leading up to, that any basis will have the same amount of vectors for any particular vector space. So here's the definition of a basis. It must satisfy 2 conditions. It must be linearly independent, and it must span the vector space that it's a basis of. For example, if B is a basis of V, then B must span V. We could write it out like this, that V is the span of B, and B must be linearly independent. We could write it out like this as an abbreviation. So this is a picture of what a basis is. It's a way of representing a point in space, so that every point may be represented as a unique vector of numbers. The basis vectors don't have to be of unit length or perpendicular to each other. So let's start with the proof of part A. We'll write out the statement of the theorem here. We'll let B be a basis of B. B contains these elements, and it contains n of these elements. And because B is a basis, it has these 2 qualities. It spans V, which can be written out as V is equal to SB, and it's linearly independent. A is a subset of V, which doesn't have to be anything in particular. It could be linearly dependent or linearly independent, and it could span A or not. And this is what A looks like. The important thing here is that A has more vectors than B, and has the minimum amount of vectors necessary to have more vectors than B, which is n plus 1. So we're required to prove that this set A is linearly dependent, to prove part A of this theorem. And each vector in A can be written out as vectors in B like this, with these constants. They are written with 2 indices because we're going to make them part of a matrix. And so we can write out all of the vectors in A in terms of the vectors in B, like this, as a system of equations. So we have to find a non-trivial solution to the constants C1 to Cn in this equation to show that A is linearly dependent, because that's its definition. So a non-trivial solution must be found that is a solution where not all of these constants are 0, so that A can be proven to be linearly dependent, and this will be enough to prove part A of this theorem. So now we'll substitute the system of equations that we got on the previous page into the equation at the top of this page to give us this. So we'll get an equation with only the basis vectors in set B. And we can gather like terms together, so we'll have an equation where we'll get a constant expression multiplying each vector in B. And we know that B is linearly independent because it's the basis of a vector space. And so we can get this expression because by the definition of linear independence, all of the constants must be 0. We can then manipulate this expression to be a system of equations. And then we can pack all of this up into a matrix equation, where the C constants will separate out into a vector. Now looking at this matrix equation, we can see that it's a homogeneous equation with more unknowns than knowns, and therefore it has a non-trivial solution, which is a solution where not all of the values of C in this vector are equal to 0. That is, they aren't all equal to 0 at once. And so A is linearly dependent, which proves part A of this proof, that any set with more than n vectors is linearly dependent. It might be helpful to take notes or look back over the proof to see what we needed to prove. So now I'm going to expand part A to include all spanning sets of V, and the only spanning sets left are those that are linearly dependent. I'm doing this to avoid confusion, because even though it's very obvious, if we invoke part A by another part of this theorem, then it might seem confusing and put the readers off, so I'm going to prove it now. If we add another vector to a linearly dependent set of vectors, then it'll still be linearly dependent. This is because it will contain all of the same vectors that cause linear dependence. We can keep on adding as many vectors as we like, and the set will always be linearly dependent. So now A can be extended to include all spanning sets, which include both cases, spanning sets that are linearly independent and are therefore called basis sets, and spanning sets that are linearly dependent, so that all possible cases of spanning sets can be included in this proof. So I'll just write out a proof of B. We'll define a set C to be a spanning set of V like this, with these vectors. And C will be linearly dependent. It will be the other case of a spanning set that is linearly dependent. So if we write up this equation here like this, then solving for all of these constants will give a non-trivial solution, so that not all of these constants will be zero. So then if we add another vector to this set, then this set will be linearly dependent too, because it will contain all of the vectors that cause linear dependence, because we can always have zero for the coefficient of the vector that we added, which was y, to satisfy the linear dependence equation. This is the equation that needs to have a non-trivial solution for all of the coefficients of the vectors, even if y is linearly independent of the rest of the vectors in the set. We can always give it a coefficient of 0, and the rest of the coefficients already have a non-trivial solution without needing y. Now to prove part C of this theorem, which relies on the expanded version of part A, which is part B. A spanning set needs at least n vectors, which is how many vectors were in a particular basis of V. Now to prove this, we'll let C be a spanning set of V. And this is what C looks like, and it contains m vectors. And to prove this part of the theorem, we need to prove that m is greater than or equal to n. So we'll use a contradiction. We'll assume that m is less than n, and see why it can't happen. So now we'll use the proof from part B, since C is a spanning set. Then having more vectors than n would cause it to be linearly dependent for any spanning set, not just the basis. But the basis set B has more vectors than the spanning set C. So the basis set must be linearly dependent. But B is a basis for V, and any basis must be linearly independent. And this is a contradiction, since B can't be both linearly independent and linearly dependent simultaneously. And so m can't be less than n. And we can rewrite this as m must be greater than or equal to n, which finishes part C of the proof, because we've shown what was required. Now to prove part D of this theorem, that any linearly independent set must have at most n vectors. We'll set C to be this set of vectors, with the number of vectors in this set being set to P. And to prove this, we're required to show that P is greater than or equal to n. And we can invoke part A of this theorem pretty much immediately. It's interesting to note that part D is the contrapositive of part A. So this is part A of the theorem. If we swap these two conditions around and negate them, we'll get the contrapositive. And isn't LD is the same as being LI, which is part D of the proof. So part D is the contrapositive of part A, and so this proves part D. Now to prove part E, the last part of the proof, and the part that we're leading up to, which says that every basis of a vector space will have the same number of vectors, which is set to be n here. So we'll set C to be this set of vectors and to have q vectors. We'll set it to be a basis of V so that it will span V and be linearly independent. So to prove part E, we only need to show that these two variables are equal. We can use the other parts of the proof. Part C will tell us that because it spans V, then the numbers of vectors contained in it will be greater than or equal to n, which is the number of vectors in another basis B. And part D will tell us that because C is linearly independent, then the number of vectors that it contains will be less than or equal to the number of vectors in the other basis B. So we'll combine these two conditions together, which will give us this equality, which proves part E, and so finishes this proof. So every basis will always have the same amount of vectors for any particular vector space. This seems obvious, but actually proving it was very difficult. So I decided to write this alternative proof of part E, which was the original one in the textbook. B and C can swap places because they're both bases, and so the inequality can shift to make Q smaller than or equal to n this time. So I hope that you've found this video to be helpful and educational. Please let me know your thoughts and feelings about it in the comments. Feel free to share this video. Click like and subscribe if you like this video and would like to be notified about more of them. I know that linear algebra can be painful and tedious, so I'm posting up these videos to help you with this course if you're doing it, and thanks a lot for watching.